In this video, we illustrate the use of an augmented matrix in solving a linear system, right? So here's our linear system. So I'll say consider x1 plus 2x2 plus 4x3 is equal to 1, 2x1 plus 3x2 plus 2x3 is equal to 0. And then finally, negative x1 plus x2 plus x3 is equal to 2. So here's our standard form for our linear system. 3 equations, 3 unknowns, nothing particularly interesting about this. But what we can do now using this augmented form is I can write it in the using my matrix notation. And so we're going to use the square brackets as our delimiters, right? And then now remember the first part of the augmented system, I guess you could say the left-hand side of the linear system, we simply extract the coefficients and kind of discard the variables. So the coefficients in the first equation are 1, 2, 4. Coefficients in the second equation, 2, 3, 2. Coefficients in the third equation, negative 1, 1, 1. But again, remember, that's only part of the information in a linear system. Equally important are these constants over here, right? So I'm going to use a vertical line, a solid line, just to kind of, again, distinguish between what are the coefficients and then what are our b's. And then we do this. In fact, let me make it clear that these are brackets. All right. So our goal now remember when we were using Gaussian elimination in our back substitution, the goal was to eliminate terms like kind of in this lower triangular part here, and then you leave this upper part here. So our goal is to eliminate these entries now in our augmented system, the 2, negative 1, and this positive 1, and then with the hopes of being able to use back substitution. All right, so let's go ahead and do that. Now, just like before, it is convenient to have a pivot of positive 1. So that's what we're going to do here. This will be our pivot, and we're going to use this pivot along with 2 elementary row operations to eliminate the entries below that 1 that I have circled, right? So this is our pivot. And now we're going to use our operation. So what I'm going to do is I'm going to kind of go horizontally as far as I can go and then go down, right? Okay, so we want to eliminate the positive 2. So we're going to take negative 2 times row 1, and then we're going to add that to row 2. That will eliminate the positive 2 right here in the second row, first column. Next, all I need to do is add row 1 to row 3, since this entry is just the negative of this our pivot. So I just need to add a row 1 to row 3, and then these 2 operations will produce a new augmented matrix, but this is for an equivalent system. So we end up getting 1, 2, 4, 0, 0, negative 1, negative 6. Actually, let me write the entire row here. And then the new second row becomes 0, negative 1, negative 6, negative 2. And then the new third row becomes 0, 3, 5, 3. And that's our new augmented system. And let me do my vertical line there. It's not required that you do the vertical line And again, as you become more comfortable expressing a linear system in this way, many times if you keep reminding yourself that this is a linear system and this final column here represents the constants, then that reduces the need for any kind of demarcation line here, right? Okay, so we're good. We're good to go. We're almost there. What I'm going to do now is, so we've eliminated 2 of the 3 entries that we need, right? So what is now my pivot? This is now my pivot. It's the first non-zero entry now in the second row, and I'm going to use this to eliminate the 3, right? And then we will have our system in triangular form, right? So what operation can I use to get to eliminate this positive 3? Well, my pivot is already negative, right? -1. Now a -1 pivot is pretty much it's just as useful as a +1 pivot. But what if you wanted to get into the habit of always having a +1 as your pivot? Well, in that case, we would have to use another elementary row operation, and we would have to multiply row 2 by -1 if we wanted this to be a +1. So we could do that, right? Because we have that operation. So if I take -1 times row 2, that alone produces a new augmented system. And you notice when you're using the augmented form, you have so much less to write. Like the variables that you're solving for, in this process, it's almost like they're non-existent. You're keeping track of numbers and you're doing arithmetic, keeping things organized until you get into a particular form where it becomes really easy to solve, right? So now I have this, and then what I'm going to do is multiply row 2 by -3 and then add it to row 3. So if I do this operation, -3 times row 2 added to row 3, right? Because now I'm using this as my pivot, that will eliminate this entry. All right, so let's see what that looks like. So what this means is the first row doesn't change, neither does the second row. But now I have to do my arithmetic and figure out what happens in the third row. So -3 times 1 plus 3, that's 0. We got that there. I mean, we know that's what's going to happen. We're using the correct constant in order to eliminate this, but then we just have to make sure that we do our arithmetic carefully to see what happens to the 5 and then what happens to this 3. So now we have -3 times 6, that's -18, plus 5, that's -13. So there we go. And then here, -3 times 2, that's -6, plus 3, that's a -3. And then we have this, right? And now we can use our back substitution. Now, here's another instance where when you get more, I keep saying this, but when you get more comfortable working with linear systems, we know that we're solving for x1, x2, x3, right? You might be able to look at this particular form of the augmented matrix and essentially figure out what x3 is and then work backwards and then isolate your variables, right? You might be able to do that just by looking at this form. In fact, I'm guaranteed that either you can do it already if you kind of see the pattern, or in a very short period of time you'll get that comfortable with this form. But just to show you the idea of the equivalence between the standard form and then this augmented form of a system. And if it makes it easier for you to solve for your variables, you can go back now and represent this, right, in the standard form using x1, x2, x3, and writing actual equations. For instance, this row here tells me that 0 times x1 plus 0 times x2 minus 13 times x3 has to be equal to -3. The second row in my augmented matrix is telling me that 0 times x1 plus 1 times x2 plus 6 times x3 is equal to 2. And then the first row in the augmented matrix tells me that 1 times x1 plus 2 times x2 plus 4 times x3 is equal to 1. But what happens is we typically don't write this, right? We don't write terms with 0 coefficients, right? But we had to keep track of these terms in the matrix, because you can't have a matrix where like it's null, like there's nothing there. There has to be something there, and in this case it was the fact that these 0 coefficients are here. But really we don't write this. I mean, this is what we typically write. We just write x1 plus 2x2 plus 4x3 is equal to 1. And then we write x2 plus 6x3 is equal to 2. And then in the third equation, -13x3 is equal to -3. And that's a really, again, the reason I'm showing this is just to emphasize the equivalence. In other words, going from one form to the other is useful for different things. Now I can use back substitution, right? So using back substitution, what does the bottom equation tell me? Well, all I have to do is divide by -13. Also, we could have done that up here by doing another elementary row operation. If I wanted to make this entry a 1, I would multiply by -1/13, which is the same as this operation here, dividing by -13. So there is an equivalence in terms of the algebra that you would use in your back substitution, and also the result of using a particular elementary row operation. But dividing both sides by -13 gives me that x3 is 3/13, right? And now look at this. Having these pivots of 1, it's very easy to isolate my variable. So now x2 is going to be 2 minus 6 times whatever I got for x3, which is 3/13. So this is 2 minus 18/13. Now 2/1, that's the same as 26/13 minus 18/13. And let me scroll down, just get a little bit more room. This will be 8/13. And now the top equation, again having that pivot of 1, makes it easier, or easy for me to isolate x1. And it looks like, but this system will have a unique solution. x1 is equal to 1 minus 2 times whatever I just got for x2. And then minus 4 times whatever I just got for 3/13. So let's see what we have here. We have now 1, let me write that as 13/13. Just expressing everything with the same denominator makes the arithmetic a little bit easier. This is 16/13. And then minus 12/13. And then putting that all together, we get that x1 is -15/13. So here is our unique solution to the original system. So our unique solution is the order triple, negative 15 over 13, 8 over 13, and 3 over 13, right? So again, you can see in terms of the final answer, what it looks like, there is no difference in terms of what our final answer is going to look like. It's just the route that we took to get there. And I think you'll definitely agree that when you have especially larger systems where you have lots of numbers to keep track of and there are lots of operations going on, this augmented form is a very, very convenient form to work with, right? So hopefully that sheds some light on this convenient tool and how it can be used. And I'll see you in the next video, where chances are we're going to be using one of these augmented forms yet again.